At the heart of dealing with any statistical quantity is the idea of uncertainty. And really, uncertainty is arising for any number of reasons in the real world. But when we're thinking about statistics, what we're thinking about is that we are trying to learn about some population, about the parameters in some population, on the basis of samples that we're actually able to take and observe. And anything that we calculate when we have a sample, so any statistics that we're actually going to calculate, are going to be dependent on the sample that we happen to observe. But of course, the sample that we take is going to be random in some sense, right? We don't know exactly the individuals that are going to make up the sample before we actually go out and take it. And so for this reason, anything that we're calculating when we're thinking about having sampled from data or run some experiment to collect data or collecting data sort of wherever they exist, there's always going to be sort of fundamental randomness underpinning the entire situation. And dealing with this randomness is really what we're thinking about when we're trying to do statistical inference, when we're trying to quantify uncertainty. This is the randomness that we're trying to deal with formally. So the key idea that we're thinking about here is that before we've actually taken any sample, right, so before we've gone out and collected any data, the value of a statistic is unknown. We don't know what the sample mean is going to be. We don't know what the sample maximum is going to be. We don't know what the sample range is going to be. Right? But these values, because they're unknown, they're going to depend on the specific sample we get. And so we can think about them as being random. Right? It's really no different than if you're thinking about rolling a die. Before you roll that die, the result that you're going to see is random. As soon as you've rolled the die, you know exactly what number you got. With statistics, we're thinking about the exact same thing. Anything that you can compute based on a sample is going to be random until you actually go out and do the sample, until you actually go out and collect the data. Okay, so what this means is that we can really think about statistics as being random variables. So as a reminder, a random variable is going to be any numeric quantity whose value depends on chance. So any mathematical variable that we can define who has a value that is going to be dependent on some sort of random process, we refer to that as a random variable. It's a variable whose value is random. So, common example, the result of a die roll, the number selected from a lottery, the weight of a newborn baby. Right? All of these things, before we've actually gone out and made the observation, before we've rolled the die, before we've played the lottery, before we've seen the weight of the newborn, these are all going to be random quantities. We might know something about them, right? We know the result of a die roll is going to be between 1 and 6, but we don't know specifically what it's going to be. And so these are all random variables because they take on some number, but only after a random process is performed. Statistics are any numeric quantities that are computed based on samples. So we've gone out, we've collected data, we take in those data, and we calculate something about them. So the contents of our sample are therefore random, right? So we don't know what items are going to be drawn from the population into the sample. And because we don't know what items are going to be drawn from the population into the sample, we don't know what the value of anything that we calculate based on that sample is going to be. So there is going to be sort of this dependence on what we call sampling variability. Right? The sampling variability is the fact that every single time you take a sample, you're expecting to get different observations in that sample. If you go out and you're trying to measure the average height in a population and you're selecting people at random, the people that you bring into your survey to measure the heights of, those are going to differ every single time. Right? So if you go out and select 10 random people one day, you select 10 random people the other day, you're probably not going to get the same 10 people on both days. Because of that, the sample that you actually get has this variability in it, right? If we think about doing this over and over and over again, you're going to get different samples each time. And because you're going to get different samples each time, you're going to get different averages each time, or you're going to get different minimums each time, right? So the statistics that you compute based on those samples are going to be different because every single time your sample is different. And so because the sample is random, so too will the statistics. So all of this is to say, statistics are going to be random variables. We can think about statistics as taking on some value, but that value is going to depend on chance. And that chance is arising because we don't know the contents of our sample before we go and actually do the sampling. So then we have our random variables, and what we normally talk about are drawing realizations of these random variables. The result of a die roll is a random variable, but once you roll the die, that's just some number. And so we call that result a realization from the random variable. It is one observation that we're actually making coming from this random process. And so when we're going to talk about statistics, we're going to be thinking about them sort of as a process or as a function, right? We can think about the sample mean as adding up all of the values and then dividing by the total number. And when we're thinking about it as this process or as this function, we're thinking about it as a random variable, right? So the sample mean is going to be random because we don't know what's going to be in our sample, but we do know that the sample mean is going to add up all of those values and divide by the total number, right? So the sample mean is random when thought of as a mathematical function. So the sample mean is going to be random. The sample standard deviation, right? We're going to add up all of the squared deviations, divide by n-1. That's still random because we don't know what's going to be in our sample. But once we actually go out and take a concrete sample, then we can compute some specific value. And once we've computed a specific value, that value is not random. That's a realization of the random process, right? And so once you know the specific value of the sample mean or the specific value of the sample standard deviation, those aren't random quantities anymore. Those are realizations of a random quantity. So we take a sample of size 50, the sample mean is 15. Right? 15 isn't random, it's just some number. And so in this case, we say that 15 is the realization of the sample mean. The sample mean is random, 15 is not random. We take a sample of a size 183, sample standard deviation is 8. It's the same thing. Once we know the standard deviation is 8, right, then there's no randomness left anymore. We've computed 8 based on the specific sample that we've actually gotten. So the sample standard deviation was a random variable, but then we realized it to be 8 in our specific sample. If we took a different sample, we'd get a different value than 8, but once we have that value of 8, the randomness is gone. And so really the thing to be thinking about here, right, is that think about the die roll. So the result of the roll of a die is going to be random until we actually see that result. And as soon as we actually see that result, it's no longer random, right? And so if I'm holding a die and I'm about to roll it, right, I know there's a 1 in 6 chance that I roll a 5. But if I roll the die and I see that a 5 comes up, then that's the number that we actually saw on the die. If I roll the die and it's a 3, right, there's no longer a 1 in 5 chance that that's a 5 because it's a 3. It's no longer random, right? And so before you do the sampling, your statistics are going to be random variables. After you've taken a sample, there's no randomness left over. They're just numeric quantities. They're realizations of the random variables. So we can work through sort of a formal example here to really understand where this randomness is coming from. And so right here we have a population that is comprised of 10 individuals, and we're thinking about these as being the ages of these 10 individuals. And so whatever you want to imagine this population is coming from, right, this is our full population. Maybe this is the population is some family, right? It's a 10-person family, and they're aged between 20 and 70 years old, right? And here, what we could actually do, because we have the entire population, is we could work out that on average, they're 41.9 years old, right? And so we would get this just by adding up those 10 numbers and dividing it by 10. But of course, if we didn't know that these were all 10 people from our population, we could draw samples of people from this population. And so we'll consider taking samples of size 5. And so a sample of size 5 is going to be any of these 5 ages pulled at random from these 10 numbers here. So perhaps we get 26, 54, 56, 58, and 70. Okay? And so that's a sample of size 5. All of those are being drawn from the population here, right? And if we work out that sample, we get a sample mean of 52.8. Right? And so the first thing to note, that's not exactly the 41.9. In fact, it's a little ways off of that 41.9, right? But it's sort of maybe in the same ballpark. But we expect that to happen because we don't have the whole population. We just have a sample from our population. But the critical thing to note is that this is just one sample of many that we could have seen. Right? And so we could have equally likely had seen 26, 30, 39, 54, 58. And this would have produced a sample mean of 41.4. This sample is no more or less likely than the previous one. In this case, our sample means a lot closer to the truth than in the first case, right? But this would have just come up by taking sort of a different sample, right? And we could work through this and see sort of alternatives, right? So here's a sample that gave you a 44.8 average. Here's a sample that would have given you a 41. The key thing to note is that the sample mean is going to be depending on random chance, where that randomness comes based on who gets included inside of that sample. We don't know which 5 members of the population we're going to see until we've gone out and collected them. And because of that, we don't know the value of the sample mean until we've gone out and collected our sample. So the sample mean is random, right? It's going to be some set of 5 people are going to be brought into our sample, and the sample mean is going to be their average, right? And as soon as we actually do that process, we can easily work out what is the mean. And at that point, that's a realization of the random statistic. So the sampling variability, the fact that every single time we take a sample, we're going to get different values in there, that's what's causing all of the randomness that we're trying to deal with. So there is sampling variability, which just means between samples, we have variation in what's actually going to be observed. And that's because the members of our sample are going to be random draws from the population, right? So when we're thinking about where is the randomness coming from in a statistic, it's coming from the fact that samples themselves are random. So because a statistic is a random variable, right, it must have a distribution. Anything that is random has a distribution. And so because statistics have randomness that arises through the sampling variability of the statistic, then it must mean that they have distributions. And understanding the distribution of a statistic is going to be key in order for us to start to quantify uncertainty and actually do statistical inference.